Howdy. I wanted to continue our discussion from today about Euler's number E. You remember that we said that Euler generated his number by considering what happens to interest rates when the compounding is made continuous. That is, when the number of compoundings is allowed to increase without bound. And what Euler discovered, and what we discovered to our great surprise, is that this limit is not 1, nor is it infinity, but instead it is an irrational number whose first few digits are 2.71828.8284 dot dot dot. Notice that this is an irrational number. It does not come to an end in its decimal expansion, and nor does it repeat. Now, I want to do the following things. First of all, I'd like to rewrite E using a substitution. And then I want to use that to consider the function f of x equals e to the x, which is an exponential function, just as we talked about today. And third, what I'd like to do is I'd like to try to find the derivative of e to the x. So let's do each one of those. First of all, I want to take our definition here. E equals the limit as n goes to infinity of 1 plus 1 over n to the n power. And I'd like to rewrite this definition by pulling off a substitution. Let's let z equal 1 over n. Now, I just pulled z out of the hat. It's just a variable here. So we're going to let z equal 1 over n, and I'm going to use substitution to replace everything in my limit, my definition of e, in terms of z. Well, if z is equal to 1 over n, then pretty clearly n is equal to 1 over z. And so the expression 1 plus 1 over n to the n is the same as the expression 1 plus z to the 1 over z. But also, as n goes to infinity, then z is going to go to 0. Let's check that. The limit as n goes to infinity of z is the limit as n goes to infinity of 1 over n, which is equal to 0. And there you have it. So we have a second way to write the value for e. At this point, it might be worthwhile if you were to grab your calculator and pause this recording for just a moment and check that this limit actually works out by choosing a small value for z. For example, you might choose z equals 0.0001 and just substitute it into the expression right there and see what you come up with. Pause the recording at this time, substitute, and come back. Welcome back. I hope you are satisfied that you got a number that was close to e. Well, the reason this is going to be helpful to us is that we are going to now define a function, an exponential function. F of x equals e to the x. And we're going to do it like this. We're going to say that e to the x is the limit as n goes to infinity of 1 plus x over n to the n power. Now you say, that doesn't look very much like an exponential. And I think you're right. It doesn't look very much like an exponential. But let's do the same substitution that we did before. But with a small twist, let's let z equal x over n. And once again, if z is equal to x over n, then n is equal to x over z. So that I can rewrite my limit as the limit as z goes to, let's see here, what will z go to as n goes to infinity? As n goes to infinity, z will go to 0. Z is equal to x over n, so we can substitute there. And n is equal to x over z, so we can substitute here. Now here's what I want you to observe. Using our exponent property of limits, I can rewrite this limit as the limit as z goes to 0, 1 plus z to the, here it is, using exponent rules, just like that. And what is this limit equal to on the inside? Why, we just showed that that limit was equal to e. So it turns out that our definition right here actually makes a whole lot of sense. In terms of the substitution z equals x over n, this limit gives me exactly e to the x power. Now, because it is an exponential, and because e is bigger than 1, remember that e is 2.71828 something something something, which is bigger than 1, then that means that we can actually say a whole lot about the graph of e to the x. You remember from class today that an exponential function is going to have a 3-point solution graph. We're going to go through the point 0, 1, because e to the 0 is 1. We're going to go through the point 1, e, because e to the 1 is obviously e. And also, the limit as x goes to negative infinity of e to the x is going to be 0, so that we will have a horizontal asymptote y equals 0. And there's our graph of e to the x. So that's pretty nice. We also can observe that e to the x is going to obey the same 3 exponential rules that all exponential functions obey. The product rule, the quotient rule, and the power rule. Just like so. So this just raises an interesting question, and that is, what is the derivative of our exponential function? To get at that, I need to share with you our third special limit for the year, and in fact our last. It's possible to do this limit analytically, but I don't think the details are very enlightening. Instead, what I'd like for you to do is to evaluate this limit on your calculator. Get your graphing calculator and find the value of this limit for me, and pause the video while you do so. Welcome back. If everything went well, then you should have found that this limit has a value of exactly 1. Let's check that. I'll pull up my calculator. Wait for just a moment for it to validate the software license. And we'll let y equal, look at this, we'll let y equal e to the x minus 1, all of that over x. And when I graph this in a suitable window size, like so, and I evaluate the limit by choosing x values that are close to but not equal to 0, such as 0.00001, then I get a y value that is obviously very close to 1. And that's true on both sides of 0. If I choose a negative 0.0001, then I also get something that is obviously very close to 1 right there. And so that's sufficient evidence for us to say that this limit is probably 1. And if you'll just take my word for it for a little bit, that this limit is exactly 1, then we should be good. Now, how does this limit help us? Well, because if I want the derivative of the exponential function e to the x, then, because I lack a derivative rule, I'm going to have to use the limit definition. And when I do, the limit definition looks just like this. The limit as h goes to 0 of f of x plus h minus f of x, all of that over h. So, now where can I go from here? Well, looking at the expression on the top, I observe that I do have an exponential rule that will cover this case. I can rewrite e to the x plus h as e to the x times e to the h. And now a miracle occurs because my top terms have a common factor of e to the x that can be factored out. Notice that e to the x is a constant with respect to h because it does not depend upon h. And when I do factor out that common factor, what I'm left with is the limit as h goes to 0 of e to the h minus 1 all over h. But this is exactly our special limit that we discovered up here. So this limit goes to 1, and what I'm left with is e to the x times 1, so that the derivative of e to the x is itself. Look at that. The derivative of e to the x is exactly itself. Now please notice, beginning calculus students will get this confused with the power rule, and they will try to use the power rule on this expression, and they'll try to come up with something silly like x times e to the x minus 1. No, no, 1,000 times no. The reason that does not work here is that our exponent is variable. It is changing. It is x. So as x changes, that exponent changes. And as a result, we should not expect that a rule that depends upon constant exponents, the power rule, should also apply to something for which the exponents are variable. It does not. Instead, this is the proper derivative rule for e to the x. Now this may raise a second question in your mind, which is, what about the other exponential functions? And for that, you'll have to come to class tomorrow. Well, I hope this has been helpful.